Welcome, ladies and gentlemen, to Integrated Math 2. In today's episode, we will be discussing Chapter 4.1.3, which is factoring more quadratics. Ultimately, this chapter really focuses and hones in on the drilling of the factoring. In the last couple sections, we learned about how the area model can be used to represent a quadratic expression, which is what each of these four expressions are. And we will be practicing how to ultimately use that area model. And we explored the connection of the diamond method with the area model to see how they all work together to get us from an area as a sum to an area as a product. So let's just go ahead and start off with A here. We start off with the quadratic x squared plus 6x plus 9. I'm going to go ahead and just make a diamond problem real quick here. I'm going to throw the 9x squared up top, right? And I get that by multiplying the x squared and the 9. I'm going to throw down the 6x on bottom. That's the middle term, and the middle term will always go down in the bottom. The top term will always be the first and last term multiplied together. And now I have to look for two numbers that add up to 6x and multiply to 9x squared at the same time. Hopefully that's obvious. I'm going to throw in a 3x and a 3x. And what that does is it gives me now my area model dimensions. My x squared from the original will go in the bottom left. My 9 from the original will go in the top right. 3x and 3x will throw down. I've got x plus 3 and x plus 3. Again, what am I doing? I'm just finding the dimensions of this rectangle. And that is how I'm going to get my area as a product, which is ultimately going to end up becoming x plus 3 for the base and x plus 3 for the height. Now, this idea here, I can actually, because they're the same, I can actually call this a culmination of x plus 3 squared. And that is because this trinomial here, or this polynomial, or this quadratic, is known as a perfect square trinomial. Please remember that term here, a perfect square trinomial, which is basically when both factors are identical. Both factors are identical, and they create the perfect square trinomial. And again, let's just talk about what that trinomial is again. The trinomial three-term expression is going to be x squared plus 6x plus 9. We will eventually explore the relationship between the 6 and the 9 right there and other perfect square trinomials, and we'll establish a numerical pattern between them to see how they're all related, because we'll be creating perfect square trinomials before you know it. In part B here, again, I'm going to go ahead and throw it on the x. Again, how do I get my top term? I take my first and last terms again, multiply them out. I get 6x squared. I throw on a 5x on bottom. Two numbers that multiply to 6 and add to 5 at the same time are going to be 2x and 3x. Those are going to be what goes into my area model here. So I got 2x squared and 3. I'm going to throw out my 3x here and my 2x here. Again, it doesn't matter where I throw it onto the 2x and the 3x. It's only going to impact where I throw it on my dimensions. Because my 2x is on top, it makes sense my 2x goes here and my x goes here. And then 3 is going to go and 2 is going to go, or rather, 1. And what I end up getting is 2x plus 3 times x plus 1. All right, let's go and take a look at C. With C, I'm going to go and throw it on the diamond here, and that's going to be a -7 and a 5. Now, one of the things you're going to start recognizing pretty quickly, especially when it comes to the diamond, is that if the quadratic is not factorable, you're going to find out pretty quickly when you throw it on the diamond, because the last time I checked, if I throw it on a 7, it'd be a 7x squared and a 5x, I cannot think of any two numbers that multiply to -7 and add to 5 at the same time. I mean, just 7's a prime number, so the only number that works is really 7 and 1. And no matter what order I put it in, I don't think that's going to get me to 5x. And so I don't believe this is factorable, so we'll just put not possible. And don't worry, we will learn a method for dealing with this in a quadratic equation. It is actually very much related to this perfect square trinomial. But when we get there, we will get there. And until then, I guess I'll just have to hold you in suspense. All right, in the last part here, D, again, we're going to multiply the ends together. So negative 14 times 3 is going to be negative 42m squared, and then a positive m down here. Two numbers that make that happen are going to be negative 7m and positive 6m. Oops, not 6x, 6m. And now I'm going to go ahead and throw that down into my area model. Again, how does this work? The negative 7 plus 6 is going to get me m. So let's go ahead and take a look at D here. And again, we will go ahead and file this into our diamond. What we'll do is we'll have 3m times negative 14, which is going to be negative 42m squared. I'm going to get a positive m on bottom. So I'm looking for two numbers that multiply to negative 42 and add to positive 1 at the same time. My gut is telling me a positive 7m and a negative 6m are going to do it. And so again, those numbers help me construct my area model. So what I have is 3m squared and negative 14. Again, it won't matter which way I throw down the 7 and 6. So I'll go and throw the 7 down here. I haven't done that ever. And I'll throw the negative 6 here. And so again, all it does is it just impacts what my dimensions go in. But again, because I'm multiplying base times height, it won't matter what order I multiply them in, because in multiplication, the order doesn't matter. So I'll throw down my 3m here and my m here. Hopefully that makes sense, right? Because the 3 has to interact with the negative 6 through a negative 2. The m can get multiplied by a 7, and there we have it. There we have our area as a product. So go and hang on. I'll be back with the next set of problems. In 4-25, it says you have been working with quadratic expressions written in the form ax squared plus bx plus c. But what if a term is missing, or what if the terms are in a different order? Consider these questions while you work with the expressions below. Share your ideas with your teammates and prepare to demonstrate for the class. So when things are missing, all that means is that things in your area model will be missing. So if you notice 9x squared minus 4, you could write it as 9x squared plus 0x minus 4. So we got that placeholder in for the middle term that's missing. And now that can kind of go in and fill in the void of the diamond problem here. And so now we have to think of two numbers that multiply to negative 36x squared and add to 0x. Well, that shouldn't be too hard. I believe negative 6x and 6x will do that. And then in the diamond, what we'll have is we'll just have a 9x squared and a negative 4, and then negative 6x and 6x. So we end up getting 3x and 3x. And I broke up 9x squared that way because they both have a 6 on the adjacent sides. And then that's going to end up becoming minus 2 and plus, oops, backwards. Looks like plus 2 here and minus 2 here. And so what I've got is 3x plus 2 times 3x minus 2. Now, it's very similar to that perfect square trinomial that we had before. If you look at the x plus 3 times x plus 3, this one, however, is 3x plus 2 times 3x minus 2. This is what's known as a difference of squares. And the reason why it's called that is because if you look at the original expression, 9x squared minus 4, if you know your perfect squares really, really well, you'll notice that 9x squared is a perfect square, and so is 4, right? This could kind of be seen as 3x all squared minus 2 squared. Now notice the 3x has a relationship with the first terms here, and the 2 has a relationship with these two terms on the back end. It's known as a difference of squares. It is not the same as a perfect square trinomial. Please be careful. People mix those up all the time. Don't be like those people. But when we get into more fast ways of factoring, recognizing the difference of squares and the perfect square trinomial, I think, is going to be very, very helpful for you. It'll help you factor things very, very quickly. So yeah, there you go. There's a difference of squares for you. And so from here in B, notice how you've got 12x squared minus 16x. If I decide to go throw in a plus 0 right here, Well, what am I looking for? If I throw it on the diamond model, if I multiply the two end terms together, I have 0. And then the bottom term is going to be 16x, or negative 16x, which means all I can do is just get negative 16x and 0, because the only way I'm going to get 0 up top is if I multiply the two ends to get 0. So what that's going to do for my area model is it's going to throw down a 12x squared and a 0 here. I feel like I can only really throw down a 16x and a 0 here. So I feel like with this, the way I'm going to throw this down is I'm going to go ahead and say, all right, well, I believe this is going to be 4x and 3x, right? And I got to throw the 4 down there because of the whole negative 16. So I'm thinking negative 4 here, and I'm thinking 0 here. So I think it's just going to become 4x plus 0 times 3x minus 4. Now, this could actually be shortened up into 4x times 3x minus 4, which almost looks like the distributive property because it is. And we will eventually learn this method of what we call greatest common factor, which is going to be faster than the area model when you can see that both of these terms have actually a 4x in common that can be literally divided out. But we'll talk about that in a future video. With C, on the other hand, this is a pretty conventional problem, except it's out of order. It's 3 plus 8k squared minus 10k. Well, that's okay. Just go ahead and, go ahead and just put it in order. And now we're back to our good old buddy, the area, or the diamond problem and area model. So let's go and throw that down. Let's see, that's going to be, it looks like 24k squared and negative 10k. So again, we're going to look for two numbers that multiply to positive 24k squared and add up to negative 10k. That's going to be negative 6k and negative 4k. So in our good old buddy, the area model, I'm going to get 8k squared and a 3. I'll go and throw down the negative 6k and the negative 4k here. So again, if I'm going to break apart an 8k squared, I'll go and break it apart as a 4k and a 2k. That gives me a minus 3 and a minus 1. And what I get is 2k minus 1 times 4k minus 3. And I think that's going to be good enough for this guy. And in D, it looks like it's 40 minus 100m. Okay, so again, if we throw on the area model for this guy, well, remember, if I throw down, let me go and write him down real quick. If I do negative 100m plus 40 now, I can almost see that as 0x squared times that. So how does this pan itself out? Well, that's going to be a negative 100m. That's going to be a 0. And I'll go and throw out a negative 100m and 0 here. And so in the area model, it looks like this is going to be 0x squared, 40. And then I'll go ahead and throw down my negative 100m here and my 0 there. And so what I end up with is, I'm going to throw down a 5 here and an 8 here. And the reason why I'm doing that is because 5 times 8 is 40. Now, the 5 times something is going to get me 100m, which is going to be negative 20 right here, negative 20m. And so what I have is I have 5 times negative 20m plus 8. Now, this thing isn't quite done, but when we get to greatest common factor in the next unit or in the next section, I will definitely let you guys know about that. So that will wrap up this drill and kill session of the factoring quadratics. Hopefully you found this useful. As always, please leave comments or questions in the comments area, and I will see you all in the next episode.